Welcome to NeuralMonk's AI Systems and Architecture series. Today we explore vector databases, the memory layer that powers modern AI. A regular database stores rows and columns, and answers queries like, find all users where name equals John. A vector database stores lists of numbers called embeddings, and answers queries like, find everything similar in meaning to this sentence. This distinction sounds small, but it enables an entirely new category of applications: semantic search, recommendation engines, image similarity, and most importantly, retrieval-augmented generation for large language models. By the end of this video, you will understand exactly how vector databases work from embeddings all the way to production deployment. Before we can understand vector databases, we need to understand embeddings. An embedding is what you get when you pass text, an image, or any piece of data through an AI encoder model. The output is a list of floating point numbers. For example, the word king becomes a vector like 0.82, 0.14, 0.97, and so on for 1500 dimensions. The brilliant property of embeddings is that semantically similar items produce numerically similar vectors. King and queen have nearly identical vectors because they share most of their meaning. Both are royalty, both are nouns, both are formal titles. Apple has a very different vector because it is a fruit, not royalty. This is the foundation of everything a vector database does. It stores these vectors and lets you search by similarity rather than exact match. Now that we have embeddings, how do we search through millions of them quickly? The naive approach is brute force. Compare your query vector against every stored vector one by one. With 1 million vectors at 1500 dimensions each, that is 1.5 billion multiplications per query, far too slow for real-time use. The solution is approximate nearest neighbor indexing, specifically an algorithm called HNSW, which stands for Hierarchical Navigable Small World. HNSW builds a layered graph. The top layer is sparse, a highway with only a few nodes connected to each other. The bottom layer is dense, the full graph of all vectors. To search, you start at the top layer, navigate greedily to the nearest node, then drop down to the next layer and repeat. This gives you O log n search time instead of O of n, making a query against 10 million vectors take just 2 to 5 milliseconds. A vector database is made of 3 distinct layers working together. The vector store is the bottom layer. Raw float arrays persisted to disk or SSD, sharded across nodes for large datasets. The ANN index sits in memory, an HNSW graph of vector IDs and their relationships. This is what makes search fast. It is rebuilt from the vector store when the database restarts. The metadata store sits alongside. Each vector has associated JSON fields like date, author, category, or source URL. These allow you to pre-filter or post-filter results before or after the ANN search. When you insert a new document, the right path is, embed it, store the vector to disk, insert into the HNSW graph in memory, and return the vector ID. When you query, the read path is, embed the query, run ANN search for top K matches, apply metadata filters, fetch the raw text, and return ranked results. The most important use case for vector databases today is Retrieval-Augmented Generation, or RAG. Here is the problem RAG solves. A large language model has a fixed context window, between 4,000 and 128,000 tokens depending on the model. It cannot fit your entire knowledge base in one prompt. RAG solves this by storing all your documents as vectors in a vector database, then at query time retrieving only the 3 to 10 most relevant chunks and injecting them into the prompt. The LLM then generates its answer based on retrieved facts rather than memorized weights, dramatically reducing hallucinations and enabling real-time knowledge without fine-tuning. The quality of RAG depends heavily on chunking strategy. Chunks of 256 to 512 tokens with 50 to 100 token overlap work well in practice. Overlap prevents important sentences from being split across chunk boundaries. There are now 5 major vector database options, each optimized differently. Pinecone is the managed cloud option, fully serverless, scales to over 1 billion vectors, and is the most popular choice for production RAG pipelines. Gdrant is the best open source option, written in Rust, extremely fast, with powerful payload filtering that beats most competitors on recall with metadata filters. Weaviate offers a GraphQL interface and native multimodal support, useful when you are working with both text and images in the same index. ChromaDB is the go-to choice for local development and prototyping, extremely easy to set up, integrates directly with LangChain and LlamaIndex. Vector is a PostgreSQL extension. If your application already uses Postgres, Vector lets you add vector search without a new database, though it tops out around 10 million vectors before performance degrades. The decision rule is simple: prototype with Chroma, go to production with Gdrant, and move to Pinecone when you hit hundreds of millions of vectors. You now understand vector databases from first principles. Embeddings encode meaning as distance in high-dimensional space. Similar items produce similar vectors. Approximate nearest neighbor search, specifically HNSW, lets you find similar vectors in milliseconds across millions of entries. A vector database layers 3 things: raw vector storage on disk, an ANN index in memory, and a metadata store for filtering. RAG uses a vector database as the external memory for a large language model, retrieving relevant chunks at query time to ground answers in facts. The right tool depends on your scale: ChromaDB for local work, Gdrant for production open source, Pinecone for enterprise scale. Vector databases are not just a database technology, they are the backbone of the AI memory layer that powers every serious RAG application in production today. Subscribe to Neural Monk for weekly deep dives on AI systems and architecture.